Look at almost any tractor, and one thing seems completely out of proportion: enormous rear wheels, paired with much smaller ones up front. Most people assume they are simply bigger because the tractor is heavy or needs more grip. But if that were the whole story, why not make all four wheels the same size, or just make the rear tires wider? The real answer is hidden in what happens between rubber, soil, weight, and torque every time a tractor starts pulling. Subscribe for more hidden engineering like this, because those giant wheels are solving a problem you can't even see from above. The giant tire is really a pressure regulator. At first glance, the explanation seems obvious. Tractors are heavy, so they need enormous tires. But that is only part of the story. The real engineering challenge is not simply supporting thousands of kilograms. It is controlling how that weight reaches the ground. A tire carries the tractor through a contact patch, the small area of rubber actually touching the soil. Make that patch larger, and the same load is spread over more ground. That lowers the pressure concentrated near the surface. Agricultural tires are designed to work at relatively low inflation pressures, allowing the sidewall to flex and the footprint to grow. A larger tire can carry substantial loads at pressures that would be impractical for a much smaller tire. That matters because farm soil is not pavement. Beneath the surface are pores filled with air and water, channels formed by roots, and spaces that allow new roots to grow. Concentrate too much pressure in one place, and those spaces begin to collapse. Water infiltration gets worse. Roots meet more resistance. The damage may remain invisible from the cab. So the huge rear tire does not magically make the tractor lighter. It changes how the tractor's weight is delivered. There's an important limit, though. Large, low-pressure tires are especially useful for reducing surface pressure and shallow compaction, but they cannot erase the effects of a very heavy axle deeper underground. The tractor is still heavy. The trick is making that weight touch the field as gently as possible. Why not just make the tire wider? If spreading the load is so important, there is an obvious question. Why build a rear wheel that can stand taller than a person? Why not simply make the tire wider? Because width is only one dimension of the footprint. A large diameter tire can create a longer contact patch in the direction of travel, and on soft ground. That length matters for reasons that go beyond pressure. A tractor tire is not rolling across a perfectly rigid road. It is constantly deforming the surface beneath it, sinking slightly, compressing soil and pushing material out of the way. Imagine a small wheel dropping into a shallow rut. To keep moving, it has to climb out at a relatively steep angle. Repeat that thousands of times across a field, and some of the tractor's power is being spent simply overcoming the terrain created beneath its own wheels. A taller wheel approaches the same depression at a shallower angle. It rolls over irregular ground more smoothly and tends to encounter less severe resistance from the soil in front of it. In terra mechanics, wheel diameter, sinkage, and soil deformation all influence rolling resistance on soft surfaces. This is why tractor tires are not merely wide flotation devices. Their diameter is doing real work. A wider tire helps spread the load sideways. A taller tire extends that footprint forward and backward, while also improving how the wheel rolls through soft, uneven ground. So those giant rear wheels are solving two problems at once: keeping the tractor from pressing too aggressively into the soil and keeping the soil from stealing unnecessary power as the tractor moves. The perfect tractor tire is supposed to slip. Here is where tractor physics becomes strange. You might assume the perfect tire would grip the ground so well that it never slips. On pavement, that sounds reasonable. In a field, it is not. Agricultural tires actually need some wheel slip to develop useful pulling force. For heavy drawbar work, commonly cited efficient ranges are roughly around 8 to 15% depending on the soil, tractor configuration, and field conditions. Zero slip is not the goal. The reason is hidden in the tread. Those deep-angled lugs are not simply rubbing against the surface like a car tire on asphalt. They enter the soil and push against it. The soil deforms slightly. The tread shears through it. That interaction generates the horizontal force that pulls the tractor forward. Too little slip can mean the tractor is not making full use of its available traction. Too much slip is worse. The tires spin, soil is disturbed unnecessarily, fuel is wasted, and forward speed drops. The large rear tire helps keep the tractor inside that useful middle ground. Its long footprint allows more tread bars to engage the soil at the same time. Lower inflation pressure can lengthen that footprint even further, giving the tire more opportunity to transfer torque before the soil gives way. So when a tractor crosses a field, the tire is not trying to behave like glue. It is performing a controlled exchange with the ground. Bite, deform, push, release. A little movement between tire and soil is part of the process. The engineering challenge is making sure that little bit of slip stays little. Pulling a plow makes the rear wheels heavier. Look at a tractor parked in a field and its weight distribution appears fixed. The engine, transmission, cab and ballast all sit where the engineers place them. Then the tractor starts pulling. The moment a plow, cultivator or other implement begins resisting forward motion, forces travel through the hitch and into the tractor's chassis. That pulling force can create a pitching moment that transfers additional load toward the rear axle. Experimental tractor testing has measured increases in rear axle loading under drawbar pull with the exact amount depending on tractor geometry, hitch position, ballast, and the implement being used. And the hitch itself can add even more. A 3-point mounted implement can place substantial weight directly onto the rear of the tractor. Trailed equipment can also apply vertical tongue load. Suddenly, the rear tires are dealing with more than the tractor's static weight. They are sitting at the intersection of 3 demands: high traction, dynamic weight transfer, and implement load. That changes the way you should look at their size. Those rear tires are not enormous simply because designers had unused space behind the cab. They are located where some of the greatest forces in the entire machine converge. And there is a useful feedback effect. More load on the driven rear axle can increase the tire's ability to generate traction, provided the soil can support it and the tires are correctly inflated. But too much load raises soil stress and rolling losses. So farmers and engineers spend real effort balancing tire pressure, ballast, and axle loading. The tractor is not simply pulling an implement. It is constantly managing where thousands of kilograms press into the earth while hundreds of horsepower try to move the machine forward. The front wheels aren't just for steering. The classic explanation for a tractor's strange proportions is simple. Big rear wheels provide power, small front wheels steer. That explanation works surprisingly well for traditional two-wheel drive tractors. But modern tractors complicate the story. Many now use mechanical front-wheel drive, often called MFWD, which means the front axle also receives engine torque. Those smaller front tires are no longer passive wheels being pushed across the field. They are helping pull the tractor. And that creates a fascinating engineering problem. The front and rear tires have very different diameters, so they travel different distances with each revolution. The drivetrain, therefore, has to coordinate their rotational speeds through carefully selected gear ratios and tire sizes. Manufacturers use the rolling circumference of the front and rear tires to calculate whether the combination is compatible. On an MFWD tractor, engineers typically want the front axle to run slightly faster than the rear in terms of theoretical ground speed. This is known as front wheel lead. In some manufacturer examples, the target is only a few %. Too little lead can reduce the benefit of front-wheel drive. Too much can create tire scrub, drivetrain stress, and unnecessary wear. So the front tires are small for more than one reason. Smaller dimensions help preserve steering clearance and maneuverability around the engine and chassis. Meanwhile, the rear axle can accommodate the enormous footprint needed for the tractor's highest tractive loads. But mechanically, the two ends of the tractor are connected. Think of the front and rear tires as two differently sized gears touching the ground, synchronized by the drivetrain. Their proportions may look mismatched. In reality, they have to work together with remarkable precision. Those giant rear wheels are not oversized by accident. They are the result of a machine trying to do something surprisingly difficult, turn enormous power into useful motion without fighting or destroying the ground beneath it. And once you see that hidden physics, a tractor suddenly looks far less primitive and much more precisely engineered. Click the next video to uncover another hidden design secret. Like, subscribe, and tell us what surprised you most in the comments. Thanks for watching, and I'll see you in the next one.